Good morning, everyone. I'm Sudarshan Ambala, working as faculty in physics with Government City College, Hyderabad, Telangana. Today's topic is oscillator. Before to this oscillators, I've been following the syllabus of Osmania University CBSES system syllabus, and under that, for the final year, we have a paper called Basic Electronics. So according to the topics of that particular syllabus, I'm covering up second unit and third unit for the basic electronics. So far, I have covered up the topics called band theory of p-n junction. We have studied the insulators, semiconductors, conductors, intrinsic semiconductors and extrinsic semiconductors, pure and pure form. What are n-type and p-type semiconductors, how they are formed, pentavalent or trivalent impurities added. What is the working principle of p-n junction when connected in forward bias and reverse bias? Then the usage and few of the applications of the diodes. Zener diode as a voltage regulator, and the VI characteristics of a diode. Further application of a diode, we have studied the rectifiers, half-wave rectifier, full-wave rectifier. And to overcome the center type of the secondary coil, we have studied the bridge wave rectifier. Then if two p-n junctions are suitably added and then the new device is formed, that is called a transistor. We have covered up this topic called transistor with NPN and PNP transistor. We have seen the current components in the transistor, all the current components in the transistor. Studied the configurations, common base, common emitter and common collector configurations. The characteristics of the transistor in different configuration, input as well as output characteristics were studied. We have covered up so far all the amplification factor for common base, common emitter and common collector as alpha, beta, gamma. And because in the case of common emitter, the alpha, the beta, the amplification factor is high. That's the reason we use any transistor that too into the mode of common emitter configuration. And we use an NPN transistor because the flow of current in the circuit is because of the electrons, majority charge carriers. We have seen the biasing of the particular transistors also, a proper biasing and stabilization. Next, we have seen the amplifiers, how the low signal is converted to high signal. It can be power signal, voltage signal, input signal, current signal, anything. And especially, we have studied an RC coupled amplifier, resistance capacitance coupled amplifier. If you want to increase the gain at the output, so we can have cascaded manner. The first output of the amplifier is given as an input to the second amplifier in a cascaded manner through the coupling capacitor CC, so that the ultimate gain will be high according to our specifications. We have seen the amplifier classes like class A amplifier, class B amplifier, class AB amplifier, class C amplifier, class D to T amplifiers with the respect to conduction angle, linearity, slew rate, and efficiency, the usages and all. Again, we have seen the feedback amplifiers. The output of the amplifier, the fraction of the output is again given to the feedback circuit, and then that is small portion of the input is given to the amplifier again, so that we can have the more gain at the end of the amplifier. So we have seen the feedback amplifier, wherein in the case we can say there is a positive feedback and negative feedback. So we say positive feedback when the output signal is in phase with the input signal, then that is the positive feedback. And if the output signal is out of phase with respect to input signal, then that is called as a negative feedback. So the last, according to the CBCS system of Osmania University syllabus of the basic electronics paper, the last topic is left is oscillators. So now today's class we are dealing with an oscillators. These are the topics overview of this particular PPT. Concepts of an oscillators, Barkhusen's criteria, and the last we study about the phase shift oscillators. So we have many types of oscillators. According to our syllabus, we have only one, which is called as phase shift oscillators. Now, introduction to oscillators. An amplifier with positive feedback acts as an oscillator. I've told you what is positive feedback. If the output signal is in phase with the input signal, then that is called as in positive feedback. So, an amplifier with positive feedback acts as an oscillator. See the transfer function of an feedback amplifier, which is given as in, this is feedback gain. Feedback gain is equal to gain of an amplifier by 1 minus A into beta, where beta is called as a feedback factor. So this is a positive feedback gain. AF is equal to A by 1 minus A beta. If I have given that AF is equal to A by 1 plus A beta, then that is called for the negative feedback gain. And see that this beta is nothing but feedback factor, where A beta is equal to 1. So when A beta is equal to 1, then that condition is called as a Barkhusen conditions or criteria. And when A beta is equal to 1, then the feedback gain is equal to infinity, which is condition for the oscillation. We will see each term in the next slides. Principle of oscillators. Principle for oscillations. Sinusoidal electrical oscillations are of two types. Damped oscillations and another is undamped oscillations. So what are damped oscillations? Damped oscillations are the electrical oscillations in which amplitude decreases with time is called as an damped oscillations. Now you can see in the next slide, as with respect to as the time is increasing, the amplitude of that particular oscillation is decreasing. So this is called as an damped oscillations. Why? It is because of the loss of energy in the system producing oscillations. So because of the energy loss, the amplitude of the oscillation will be decreasing as we increase the time. So this is called as in damped oscillations. What is undamped oscillations? The electrical oscillations in which amplitude does not change with time is called as an undamped oscillation. You can see that it is constant. The amplitude is constant as we are increasing the time. So this is called as an undamped oscillation. Here you can see that the amplitude of oscillations are constant with time and there is no change in frequency. These are the oscillations which are used in various electronic equipments. These undamped oscillations are produced by providing an energy compensation circuit. Now, the circuit that produces these oscillations is known as tank circuit, shown in the next slide. This is the tank circuit. The frequency of oscillations depend upon the parameters used in this tank circuits, because we have used inductance and capacitance. Like you can see here, we have used an inductance and capacitance. The frequency of oscillation is given by the formula F naught. Here you can see F naught is equal to 1 upon 2 pi under root LC. This kind of an oscillations, basically, we are taking an example for the tank circuit when the oscillators are LC response oscillators. We have RC response oscillators, wherein the case only R and capacitance are used. And for LC combination of oscillators, like crystal oscillators, Colpitt's oscillators, Hartley oscillators, collector oscillators. So those kind of an oscillators are made up with the form of LC combination. And the RC combination oscillators are Wien bridge oscillators and phase shift oscillators. So in the case of LC oscillator, the frequency of oscillation is given with the formula of resonant frequency is equal to 1 upon 2 pi under root LC. And this is the circuit. Now let us see how it works. First, understand what is the definition of a tank circuit. A circuit that produces electrical oscillations of desired frequency is known as oscillatory circuit or a tank circuit. The circuit arrangement to charge the capacitor of an oscillator circuit is shown in this particular diagram. Okay, so we have taken an inductance and capacitance in parallel to each other. This is a switch, and what will happen if we switch on and off because of the condenser in the circuit, and how after allowing this particular condenser to its maximum charge value and decaying its value through the inductance, how the circuit behaves. Now first understand, when switch S is closed, the capacitor C is charged to the external battery potential in the direction shown. This is how it's happening when this is closed. See, it is fully charged. After attaining to the maximum charge value, it will block the further movement of charges, because once it is fully charged, or we can say that the potential difference across the two plates of the condenser is equal to the source given, the potential applied, then this we can say that it is maximum charge, and after attaining to the maximum charge value, it further blocks the flow of current through it. The capacitor discharges through the inductor L. You can see that thereby producing a magnetic field around the coil. Because it is allowed to discharge through the inductor, a magnetic field around the coil is produced. You can see here. Now the magnetic field set up around the coil begins to collapse and produces a counter EMF. This particular magnetic field begins to collapse and produces a counter EMF. The result is that the capacitor is now charged with opposite polarity. When it will give the counter EMF, then what will happen? This particular condenser is charged with opposite polarity. Here it was this particular upper plate was positive and the lower was negative, but because of the magnetic field set up around the coil begins to collapse and produces a counter EMF. That results the condenser is now changed with an opposite polarity. This have become minus and the lower plate of the condenser have become positive. This changing and charging and discharging of the capacitor results in alternating motion of electrons and produces oscillations. So how the oscillations happens? This is the basic concepts of LC response oscillators. Got it? So now, oscillators. Why we require the oscillator? Let us understand first why oscillators are necessary. In many electronic applications, electrical energy at a specific high frequency ranging from few hertz to several megahertz are required. This is obtained with the help of an electronic device called oscillator. These are used in radio, TV, radar, and other communication or digital electronic applications. We'll see each of the oscillators, how they are used with low frequency, high frequency, or mid frequency. Now, what is the definition? What is the definition of an oscillator? An oscillator is just an electronic circuit which converts DC energy into an AC energy. So simply we can say that electronic device which convert a direct or DC energy into an alternating energy can be referred as an oscillator. We also, or we can define the same oscillator as oscillator is an electronic circuit which produces an AC output without an input. So without giving any input to the particular circuit, we can have an output as an AC. Only with respect to the feedback, we can have the another circuit where the input is not given to that particular amplifier, and we can see that the oscillation have come at the output level. Before oscillator, we used to study about the alternator also. So alternator. So there is a difference between an oscillator and an alternator. What was called alternator? Alternator was nothing but an alternator is a mechanical device having rotating parts, and it converts what? It converts mechanical energy into a AC energy. So that was called as an alternator, but it cannot produce a high frequency value. That was the drawback with the alternator. Whereas if we study this oscillator, oscillator is a non-rotating electronic device which converts a DC energy into an AC energy and produces oscillations ranging from few hertz to several megahertz. That is the biggest advantage of oscillator if we compare to an alternator. So what are the basic types of oscillators we have? We have two types of oscillators: sinusoidal oscillators and non-sinusoidal oscillators. What are they? Of course, sinusoidal in the sense the output of the waveform will be in a sine wave, and non-sinusoidal waveforms are nothing but where the output is in the form of square wave, rectangular wave, or sawtooth wave. And where we can say that the sinusoidal examples are, we can say that the tune collector oscillators, Hartley oscillators, Colpitt's oscillators, negative resistance oscillators, Wien bridge oscillators, phase shift oscillators, and crystal oscillators. So these are all called as in sinusoidal oscillators. Out of all these oscillators, according to our syllabus, we have a phase shift oscillators, or we can say that RC phase shift oscillators. See the examples. Sinusoidal oscillators, a static electronic device that produces sinusoidal oscillations of desired frequency, is called sinusoidal oscillators. The example, LC oscillators, RC phase shift oscillators, example, etc. So under this RC oscillators, we will be having an RC phase shift oscillators as well as Wien bridge oscillators. And under this LC oscillators, we will have tuned oscillators, Hartley oscillators, Colpitt's oscillators, and crystal oscillators, because that all will be using an LC tank over there, a tank circuit over there. Now understand this circuit amplifier as an oscillator. So we have taken an amplifier, and the output of this amplifier, a small portion is given to the feedback, and through the feedback again we have given an input to the amplifier. So just understand this block diagram. This is an input V in and this is an output V out. This is a feedback circuit. Beta is the feedback factor, and the gain of this particular amplifier is A. So A is equal to V out by V in. We know that the negative feedback is employed in amplifiers for stability of the output. Here, the positive feedback is used to produce oscillations as shown in figure D. So here we are using a positive feedback. From the circuit, it can be observed that the amplified signal available in the circuit is AVN. See here, this is gain. So the input is AVN. The fraction of this signal, that is beta into AVN, is feedback to the input. So feedback factor is beta. So beta into AVN is nothing but feedback to the input. Now if you see that again from here, the feedback signal beta AVN must be in phase with the input signal Vn. You can observe here. So what I'm saying is the feedback signal beta AV in must be in phase with the input signal V in, so that we can say that it is into the positive feedback mode. Now the circuit starts acting like an oscillator. As defined earlier, the circuit can be shown producing an output without any input just by removing the input signal as shown in the next slide. So we were defining this oscillator in the two ways. An oscillator is an electronic circuit which produces an AC output without any input. So for that, what we did is this terminal Z is connected to X and the input signal V is removed. So there is no input signal V in V and Z is connected to X. It means there is no input. Still we can have an output as an oscillator. The circuit will look like this. This is the one. The previous circuit modified, the Z was the point and here the X was, so this are made short and there is no V in. So this is a circuit where which we can say that there is no input to the amplifier. Got it? Now how this works? Now 3 cases of feedback are possible for this case. Let us discuss them by case. If A beta, mod of A beta is less than 1, then the removal of input signal V in will result in ceasing of oscillations as per the closed loop transfer function given by this factor. So if it is less than 1, the removal of input signal V in will result in ceasing of oscillations, damped oscillations as per the closed loop transfer function given by this formula. Feedback gain is equal to gain by 1 plus gain into feedback factor. Here the output oscillations will slowly reduce in amplitude and finally die out. So what is this? This is called as in which kind of oscillation? These are nothing but a damped oscillations, because as the time is increasing, finally the amplitude is decreasing and it will come to the zero value. Such oscillator is of no use to any practical applications. Its waveform we can see in this particular diagram. So these are called as in damped oscillations, where which the amplitude is decreasing with respect to the increase in time. The second condition now, let us see the second condition. The second condition is when mod of A beta is greater than 1. Then for example, a 1 volt signal appearing initially at the input terminal will, after a trip around the loop, reappear as a still larger voltage than the 1 voltage in this case. This larger voltage then reappears as a still larger voltage and so on. It will keep happening, building the oscillations with increase in its amplitude without limit as shown in figure. So now the output of the oscillator, when the condition is mod of A beta is greater than 1, the output is in this form. There is no stability of amplitude of this particular frequency. It is called as grouping oscillations. Now the third case, if A beta is equal to 1, that means the feedback gain is equal to infinity. So what is that condition called? The condition of unity loop gain A beta is equal to 1 is called Barkhausen criteria. This condition implies that A beta is equal to 1 and that the phase of minus A beta is 0. That is, it is a positive feedback. So under this case 3, no change occurs at the output of an oscillator and we get output oscillation with constant amplitude. So these are called as an undamped oscillations when the case of when mod of A beta is equal to 1. That is nothing but a Barkhausen criteria. Clear? Okay. Thus, to obtain sustained oscillation, the loop gain A beta of positive feedback must be unity. Therefore, we can say that a positive feedback amplifier with unity gain acts as an oscillator. However, for all practical purposes in the oscillator, loop gain, that is A beta, is always taken greater than unity, and the output signal amplitude grows with time. But the non-linearity of the device limits the buildup of the signal, and steady state is attained in a short time. In the steady state, the loop gain becomes unity and the oscillations are sustained. Now we will understand what are the essentials of an oscillator. So what are how we draw the block diagram for an oscillator. The basic requirement for an oscillator circuit. An oscillator circuit, obvious, a transistor amplifier and a feedback circuit. See here, the request is of an oscillator. The block diagram, here we can see that this is a transistor amplifier. The output of transistor is given to a feedback circuit. From the feedback, it is given to an oscillator. If it is an LC response circuit, then from the oscillator circuit, it will give to the transistor amplifier. So this we can say that a block diagram with respect to an LC response, not RC. Working. An oscillator circuit contains, now you can go back and see, here you can see that an oscillator circuit contains inductive coil L, this is an L, and a capacitor C connected in parallel with each other. You can see both the components, the inductor and the capacitors, are in parallel. The frequency of oscillations depends upon the values of L and C. In the case of LC combination of all the oscillators, the resonant frequency value is equal to 1 upon 2 pi under root LC. Got it? Next, we will understand the transistor. This was oscillator circuits and transistor amplifier block. A source of energy is required to compensate the losses in the oscillator circuit. So whatever the loss happened into the oscillator circuit, that should be compensated in the transistor amplifier circuit. That source of energy is the combination of battery and the transistor working as an amplifier. So here, when we say an amplifier, we take an AC source as well as the battery, because for the negative half cycle of the AC source, for the proper biasing, we take a battery over here. So that source of energy is the combination of battery and the transistor working as an amplifier. The oscillations produced by the oscillator circuit are fed into the amplifier. So whatever the oscillators we get it from here as an output is fed into the transistor amplifier. The amplifier amplifies these oscillations. Okay, it will amplify, it will enhance the output. Then what will happen? Then what it will do? The amplified output of the oscillations is due to the DC power supplied of the battery. The output of the transistor thus obtained can be supplied back to the oscillatory circuit to compensate the losses. What is feedback role? What is the feedback? The circuit is used to feedback a fraction of the amplifier output to the oscillatory circuit. The phase of this feedback should be such that it aids the oscillations and compensates the losses. So this is how the oscillator works. As an oscillator circuit, a transistor as an amplifier, and a feedback circuit. So we can understand from this. And there are certain conditions which we have to see. Yeah, the following are the conditions requested of an oscillator to produce sustained oscillations with a constant frequency. Sustained oscillations in the sense undamped oscillations. The amount of energy supplied to the feedback circuit should be such as to meet the losses in the feedback circuit. This is the first condition. When the load is connected, it draws some energy from the feedback circuit. Therefore, equivalent additional energy has to be supplied to the feedback circuit. The applied energy should be in phase with oscillation set up in the feedback circuit. The frequency of energy supplied to the feedback circuit should be same as that of the oscillations produced by it. Now, how we will classify the oscillators? The classifications are done according to the range of frequency. So we can see that the type of oscillators, it depends on the frequency range, and audio frequency oscillators have the frequency range from few hertz to 20 kilohertz. The best example is RC phase shift oscillators and Wien bridge oscillators. Radio frequency oscillators are from the range of frequencies 20 kilohertz to 30 megahertz. Very high frequency oscillators are 30 megahertz to 300 megahertz. And ultra high frequency oscillators are which produces a range from 300 megahertz to 3 gigahertz. The last microwave oscillators are above the value of frequency 3 gigahertz. Based on the auxiliary oscillatory circuits used, we have two types. One is called as a non-resonant oscillators. The other is called resonant oscillators. Hope you all know what is resonance. When a natural frequency matches the forced frequency or forced vibrations, then we can say that the resonance have occurred. So here, what are non-resonant frequencies that are called as RC oscillators? And the example for the RC oscillators are phase shift and Wien bridge oscillators. RC in the sense resistance and capacitance. The other is called as resonant oscillators, and that is nothing but LC oscillators. In the sense, we'll be having a tank circuit, and tank circuit will consist of one inductance and capacitor connected in parallel with each other. So because of that, the oscillation takes place. And the example for this particular resonant oscillators are tuned collector oscillators, Hartley oscillators, Colpitts oscillators, crystal oscillators. We also have called negative resistance oscillators. Now, what are the applications of each of the oscillators? Like we have 6 to 7 oscillators overall. So the first is phase shift and Wien bridge oscillators are used to generate audio frequency. What kind of range it was? It was from few hertz to 20 kilohertz. Tuned collector, Hartley and Colpitts are used to produce radio frequencies. Crystal oscillators are used where high frequency stability is required. So high value of frequency, then we use a crystal frequency, crystal oscillators. If you go back and again study about the RC, these RC oscillators employ resistors and capacitors. These are more suitable for generating low frequency signals. They are also known as audio frequency oscillators. These have good frequency stability. So these are all about RC oscillators. And what are the types of oscillators? We have already seen in the back slide. Wien bridge oscillator and RC phase shift oscillator. And in the case of Wien bridge as well as RC phase shift oscillator, we will be using only resistance and capacitance. So as we don't have Wien bridge oscillator in our syllabus, we are directly shifting over to the RC phase shift oscillator. This is a block diagram. This is the circuit diagram for the RC phase shift oscillators. Now, here you can see that a phase shift circuit essentially consists of an RC network. Here this is an RC network. One RC network will produce a phase shift of 60 degree. So if we have a 3 RC networks, this R1 and RC1 will make one RC network. R2 and C2, R3 and C3 will make the last third RC network. As we are saying that one RC network will produce a phase shift of 60 degree at particular frequency value. So 3 RC network over here will produce a phase shift of total 180 degree. And that particular 180 degree phase shift is given as in this is the output of this 3 RC network as an E1. input to this is E0 and the output of 3 RC network combination is E1. This output of the 3 RC network as an input to the transistor amplifier. And for proper biasing, we use RB and R3 for a proper biasing as well as stabilization. And here we have used an NPN transistor because the arrow is moving outward to the base. It is an NPN transistor. And we can see that this particular emitter terminal is common to input section as well as the output section. It means the configuration over here is common emitter NPN transistor are used. So when we say that the input section is always in forward bias, it means there is a heavy current in the input section. If there is a heavy current, it means the resistance is very low. Whereas the output section of the transistor is connected in reverse bias, it means there will be a high impedance at the output end. So from transistor itself, we can see that this transistor is behaving as an amplifier because the input section low resistance is converted to output section high resistance value. So transistor definition itself says that transferring the value of resistance from its low to high value. So transistor basically is used as an amplifier as well as switch. For the switching, we have studied cutoff region, saturation region, and active region. The region between the cutoff region and the saturation region is an active region, and if the transistor is fully off, it was cutoff region. If it is fully on, it is a saturation region. So we have studied the transistor as a switch over there. So what it is making is the transistor itself is, transistor as an amplifier will have a phase shift of 180 degree. 3 RC network will give a phase shift of 180. So 180 plus 180, the total phase shift at the end will give a 360 degree. Okay, now we will understand each network one by one, how it makes an angle of 60 degree phase shift. So once again, we are going with the same one. You can see here, we'll go back. So this figure shows the circuit of a phase shift oscillator. It consists of a conventional single transistor amplifier. You can see here, a single transistor amplifier and a RC phase shift network. This is an RC phase shift network because we have 3 combinations of RC. The phase shift network consists of 3 sections: R1 C1, R2 C2, and R3 C3. So at a particular frequency, the phase shift of each section is 60 degree. So that the total phase shift produced by RC network will be 3 into 60 degrees, 180 degree angle. And the frequency of the oscillations is given as, for this particular phase shift oscillator, F0 is given as 1 upon 2 pi into RC into under root 6. So according to the mathematics, the resonant frequency, we will get it with the formula is equal to 1 upon 2 pi RC into under root 6, where R1, R2, R3 have to be equal, and C1, C2, C3 should be of the same value, all the condenses. Now see the operations, how the operations happens. I'll just go back to the circuit. Let us observe here only. When the circuit is switched on, it produces an oscillations. The output, this oscillated output, the output E0 of the amplifier, this is an output amplifier again given as a feedback to the input of the RC network. So the output E0 of the amplifier is feedback to the RC feedback network. We are given this E0 is an output of an amplifier which is given as an input to the RC network. This network phase shift of 180 degree and a voltage E1 appears at its output, which is applied to a transistor input. So this E1, which is an output of 3 RC network combinations, is given as an input to the transistor. Here the feedback factor is E1 by E0. And the feedback factor beta, because we are taking it in beta, should be equal to 1 by 29, which is having a very important significance. The number is beta should be equal to 1 upon 29. For self-starting the oscillation, we must have A beta which is greater than 1. It means that the gain of an amplifier must be greater than 29. Only then the oscillation can start. If you see the operations, a phase shift of 180 degrees is produced by a transistor amplifier here. A further phase shift of 180 degrees is produced because of the RC network. So as a result, the phase shift around the loop, so complete around the loop is how much we'll get a phase shift of 360 degree. Now if you see the exclusive loop, we can have here an exclusive loop, a single RC, how it is behaving now. We have taken one RC combinations. B1 is the input to the RC combination and B1 dash is the output. Okay. And if you have taken the three RC combinations, V1 is the input for this particular three RC combinations and V2 is the output. Now how it works? Phase shift, only phase shift network. This is a phase shift circuit essentially consists of an RC network. This shows, the above figure shows a single RC network. Okay. It can be shown that the alternating voltage V1 across R, this one, the V1 dash. It can be shown that the alternating voltage V1 dash across R leads the applied voltage V1 by an angle theta. So this V1 voltage is leading the input voltage V1 by an angle theta. The value of theta depends upon the value of R and C. So the output voltage phase angle is leading the input voltage V1 and the phase angle will depend on the value of R and C. So as we control the value of R, we can change the leading angle between V1 dash and V. The value of theta depends upon the value of R and C, both the components. If we change the value of R, if the R is varied, the value of theta also changes. If R were reduced to 0, if you take completely the resistance value of 0, resistance value is 0 in the circuit. If R were reduced to 0, then V1 dash will lead the V1 by 90 degree. It means if the resistance is too low or almost 0, then the V1 dash will lead the voltage V1 with a phase angle of 90 degree. So by adjusting the value of R, the theta, the value theta can be obtained to 60 degree. So it depends on us, because we want the output to be a 60 degree phase difference between input and output. So what we do, we change the value of R appropriately. Then now if we see this, now this is a single RC network. Let us understand this one now. Let us understand the three RC combinations. So this section, C figure shows the three sections. Each section produces. Now what is happening? As we have changed the value of R appropriately, this single RC network will give a phase shift of 60 degree. So three RC network will give a phase shift of 180 degrees. So the V2 leads the voltage V1 by 180 degree. Now we have a conditions. So what are the conditions? If you see back here, if you see on this particular circuit, if you consider this one, a phase shift of 180 degrees produced by the transistor amplifier. Because of this, we have a 180. A further phase shift of 180 degrees produced by the RC network. As a result, the phase shift around the loop is 360 degree. Got it? Now we can go to this slide. This is all we have seen. This is all we have seen. Yes. This because of phase shift is 180 degree transistor amplifier, and again 180 degree phase shift because of RC network. As a result, the phase shift around the loop is 360 degree. Hence, total phase shift around the loop is 0 because it's 360. Therefore, the sustained oscillations or undamped oscillations are produced in a sinusoidal oscillators at a frequency for which the total phase shift introduced as the signal travels from the input terminal through the basic amplifier, feedback network, and mixing network back to the input terminal is precisely 0 or an integral multiple of 2 pi radians. It means it is 360. And what are the other conditions? The feedback factor beta is equal to E1 by E0. It can be shown that the feedback factor of RC network is beta is equal to 1 by 29. This expression has an important significance. So for self-starting the oscillations, we must have A beta, which should be greater than 1. It means that the gain A of the amplifier must be greater than 29. Only then oscillations can start. Therefore, the sustained oscillations are not produced if at the oscillation frequency, the magnitude of the loop gain, that is the product of transfer gain of an amplifier, and the magnitude of feedback factor beta of the feedback network is less than unity. It means AB mod of AB is less than unity. Then the sustained oscillations are not produced. And what are the advantages? Let us see the advantages. We have huge advantages of this. It does not require transformers or inductors because we are using an RC network, so there is no inductors in the circuit. It can be used to produce very low frequencies. It produces good frequency stability, and pure sine wave output is possible. So these are few of the advantages of an RC phase shift oscillators, and there are certain disadvantages also. It is difficult for the circuit to start oscillations as the feedback is generally small. The circuit gives small output and it requires high voltage battery greater than 12 voltage. So we have one more issue with this frequency stability. The ability of an oscillator to maintain a constant frequency of oscillations is called frequency stability. I have differentiated few of the points how the frequency stability can be maintained with respect to few of the reasons. I have given the reasons as well as the solutions for that. What is frequency instability? Over a period of time, the output of an oscillator may not remain constant for various reasons. The change in frequency of oscillations in an oscillator over a period of time is called as frequency instability. The reasons we will discuss: oscillators in which the oscillations were produced by the oscillator circuit contain RC or LC were discussed. Now we will have the reason and the remedy for each of the frequency stability issues. Here, the frequency of operation does not remain constant. It is because of changes in the values of resistors and inductors used in the tank circuit with temperature. So what could be the proper remedy for that? In place of RC and LC oscillators, crystal oscillators can be used because it is time independent, whose output frequency remains more or less perfectly constant even if the temperature changes. So to avoid the temperature change and the output frequency stabilization, the best way to have a frequency stabilized oscillators are crystal stabilizer because it is independent of temperature. The Q factor, the operating point of an active devices. The parameters of transistor varies if its operating point Q falls on the nonlinear portion of the load line, which in turn affects the frequency stability of an oscillator. So for that, the Q point of an active device, that is transistor, is so chosen as to confine the circuit operation on the linear portion of its characteristic. The third one, inter-element capacitance. Any changes in the inter-element capacitance of a transistor, particularly the collector to emitter capacitance, causes change in the output frequency of oscillator. And for that, the remedy is this effect can be neutralized by adding a swamping capacitor across the offending element, the added capacitance being made part of the tank circuit. Power supply. Changes in the DC operating voltage applied to the active device shifts the oscillator frequency. So for that, it can be avoided by using a regulated power supply, a constant power supply. Temperature variations, if you have variations in temperature causes changes in transistor parameters and also change the value of resistors, capacitors and inductors used in the circuit. Since these changes take place slowly, they cause a slow change called drift in oscillator output frequency. So for that, transistors with heat dissipating devices can be used to avoid heating of the transistor. Output load. A change in the output load may cause a change in the Q factor of the LC tune circuit, thereby affecting the oscillator output frequency. So this can be avoided by connecting the specified or designated load at the oscillator. The last one is, we can say that there is a mechanical vibrations. So for that, since mechanical vibrations change the values of circuit elements, it results in the change of oscillator frequencies. So this can be overcome with the instability factor can be eliminated by isolating the oscillator from the source of mechanical vibrations. So this is how we can have the frequency stability. What are the applications? As we have seen, they are classified according to the frequency ranges, and but here we will be seeing the applications. So RC phase shift and beam bridge oscillators. These oscillators are used to produce audio frequency waveforms. For an example, signal generator up to 1 megahertz and function generators audio range. So normally we use function generator for the practical purposes, where which we can have an option to change the fixed value of frequency 50 Hz to any varying values. These generators are used in laboratories to test the amplifier circuits, radio circuits, TV circuits and other communication circuits. This is one picture with an audio frequency, AF oscillators. Now if you go second part like an LC oscillators. Hartley, Colpitts and tuned collector oscillators are example for the LC oscillators. These oscillators are used primarily in generating radio frequency signals, and these are used in following circuits. Radio receivers as local oscillators, TV receivers as local oscillators, for induction and dielectric heating, for high frequency applications. This is how the RF oscillators, radio frequency oscillators looks like. Few are analog and few are digital. It has got few of the peaks. The third is crystal oscillators, mainly because of the time independent we can use the crystal oscillators. And also for the higher frequency. So for higher frequency stability, piezoelectric crystals are used in place of the LC circuit in sinusoidal oscillators. Crystal oscillators. These crystal oscillators are used in the following circuits. For generation of carrier frequency in radio and TV transmitters, in electronic wristwatches, in temperature controlled ovens, in areas where high frequency stability is required. This is one of the crystal oscillators which is having a 27 megahertz. Look few of the pictures. So with this, we can say that We have covered up all the topics related to an oscillators, advantage of oscillators, the disadvantages, RC oscillators, LC oscillators, crystal oscillators. We have studied what are damped oscillations, undamped oscillations, Barkhasen's criteria when mod of A beta is equal to 1, then how it behaves. And we have taken RC phase shift oscillators with an RC network, 3 RC networks, and 1 transistor amplifier, which gives the total phase shift of 360-degree angle, and which will have the frequency values, resonant frequency as 1/25 RC into under root 6. So this was all about the oscillators. So with this, we can say that according to the Osmania University CBCS syllabus, Unit 2 and Unit 3, all the topics been covered. So thank you one and all for listening patiently all my classes. Thank you. Thanks a lot.